afternoon, everyone. My name is Angela Jamie. I'm a postdoc here at ICT, and welcome to the 10th seminar series. And just to preface today's presentation, which is a continuation of highlighting the Smart Transportation Infrastructure Initiative projects, as a brief background, STII, the Smart Transportation Infrastructure Initiative, is led by UIUC. It's a partnership between universities, public agencies, and also private partners in our hopes to lead the future of mobility for Illinois, especially in our plan of creating a new state-of-the-art testing facility, which is the Illinois Autonomous and Connected Track. As part of the funding we received from the Investment for Growth program of the University of Illinois, there are three prongs that that growth funding has been allocated to. One is the conceptualization of the track. The second one is a Master's in Professional Certification program here at UIUC, and last but not the least is to fund 8 projects per year for 3 years. And again, the idea and the premise of the projects is to aim in identifying technologies and critical use cases for IAC. And I'm happy to share the other 2 projects that we're excited to highlight today as part of the awarded STI projects last year. As you may remember, last week, Professors Hodge and Merritt shared their projects, and today we have the opportunity to hear from Professors Hovakimyan and also Professor Wang. As a few housekeeping, each presentation will be 20 minutes each, and I think Professor Hovakimyan will go first, followed by Professor Wang, and afterwards we will open up the floor for questions for approximately 10 minutes. And as your moderator, I'd be happy to involve the people we have here at our lab in Atral, and also watch out for the chat for questions that we have from the online attendees. To start, I'd like to introduce Professor Hovakimyan. She is a W. Grafton and Lillian B. Wilkins Professor at the University of Illinois Urbana-Champaign's Department of Mechanical Science and Engineering. Her research interests include control and optimization, autonomous systems, neural networks, and game theory. She received her master's degree in applied mathematics from Yerevan State University in Armenia, and her doctorate in physics and mathematics from the Institute of Applied Mathematics of Russian Academy of Sciences in Moscow. Without further ado, I'd like to transfer the floor to you, Professor Naira Hovakimyan.
Thank you for having me. Good afternoon, and let me get started without wasting time. So, if everyone sees my screen, I'm happy to get started.
Yes, thank you.
Thank you. So this is a project that's supporting my postdoc Hunmin Kim's salary partially. And so I'm presenting a work that was solely done by him. So let's move forward. So giving him all the due credit. We're looking into ensuring safety of self-driving cars as we get the opportunity to control them over the cloud network. So self-driving car industry is growing at unprecedented speed. So here are some market numbers to justify and motivate our research and keep us kind of highly motivated and to feel the pulse of the rapid development in the industry. So Black Ash Challenge is most likely well known to all of you, since we all live in the Midwest, in a place where sliding car accidents are quite popular. So Black Ash Challenge is a typical expression that's referring to the type of accidents when you will find out that it's too late to reduce your speed. So here are some kind of pictures taken what Black Ice Challenge has caused on highways when cars pile up because of this type of accidents happening. Complex environments can also cause unpredictable accidents, like slippery roads that we can have after rains, or sandy roads. So this type of roads that have patches and are not polished, are not clean, also can cause accidents when it would be too late to reduce the speed and to take control of the car. So our objective in this project is to to have adaptation to unforeseen environments, and to have safe learning of the model mismatch. Why do I emphasize safe learning? Because most of the AI methods that have become popular, they don't have safety guarantees. They have great empirical performance, but they come typically without certificates of safety and robustness guarantees. So we have two layers in our architecture. One is called proactive, the other is called reactive. And let me explain in details what do we mean by this. The proactive level is what's happening on the cloud. So there is the vehicular network that can transfer the data over the cloud about the weather conditions, about the cornering stiffness, different types of information that the cars can transfer to each other over the network, cloud network. And then there is the reactive level where there can be real-time control updates, where there can be the real-time learning. And here we have the controller working on the car. So there is the cloud level and there is the controller working on the car. So to the cloud level, we'll refer as proactive level. And the main controller that will be synthesized on the proactive level, we'll refer to it as robust adaptive control. And on the reactive level, we will have the real-time adaptation to it. So on the proactive level, so in the first half of the year, we have done some design developments for the proactive level. So let's see what's happening. This is the data center. It gets the weather forecast and it has access to the vehicular network data. So here we designed a fixed rank resilient filtering structure, which is an efficient recursive estimation of cornering stiffness for a large area. It has robustness to modeling errors. So the fixed rank filtering and the resilient estimator work together here, to which we refer like FRRF. So we combine these two type of filtering structures into one combined estimator, to which we refer like FRRF. So this is an efficient recursive estimation scheme for cornering stiffness for large areas. It's a spatiotemporal filter, which is important for this proactive adaptation. It has a special way of choosing hidden states that makes it different from the typical Kalman filter. And for that, we'll have to refer to our paper, which was published in a conference this year. Unfortunately, I do not have it here, but it's the same type of mechanism that's used in this paper 2010, from where we have borrowed this fixed rank filter. The resilient estimator is also from one of our papers, so it can deal with unknown large uncertainties, and it does not require a bound on information for the uncertainties. So we bring these two together. So the variables of interest can be computed according to an equation, which is like linear-like structure. So mu would be the weather information data coming through this cloud, and these are the hidden states in the dynamics, as I said. And the resilient estimator will give us an alternative way for computing these hidden states. And so basically in this fixed rank filter, we'll replace these hidden states with our resilient estimator. That's why this combined structure will refer to fixed rank resilient filtering. This helped us to significantly improve our estimation accuracy of this cornering stiffness, which helped to make this proactive adaptation level very effective. So it deals with spatiotemporal data with uncertainty in a very robust way. And here is the main theorem, and here is our paper that I said, where we have the complete formulation of it. And the theorem would state that if the noisy measurements are obtained as a Poisson arrival process, then under some mild observability assumption, the expected error is practically exponentially stable, which means that there exists a set of coefficients such that the expectation can be upper bounded with this exponentially decaying term. So here is some simulation done to show how it works. It's a model that has, for example, 5 small square areas. I'll show it on the next slide, how they look. Predictions from weather forecasts are randomly generated. So here are icy conditions, dry conditions, as you see. Noise covariances are set according to these parameters, and measurement event follows Poisson process with parameter 20. And our model system uncertainty is given through sinusoid. Here is the area. So yellow is yellow is dry and red is the wet. So prior estimation heat map this is. And we see that the FRRF performance is pretty good here. So how it behaves. So this behavior is very good, which means that the filter works very good. And then, so this for the proactive level, we also design, like I said, the robust adaptive controller, which is designed for the predicted uncertainty rate with rapid disturbance compensation. Here we use our typical L1 adaptive controller that has already proven its worth in real world demonstrations like our Learjet flights, NASA Airstar flights, F-16 flights. So I will give a brief overview of it. So for this simulation purposes, we use a bicycle model here. Front rear cornering stiffnesses, mean variance from FRRF, as you see here, the colors indicate. And the problem formulation is given a conservative bound of uncertainty in the environment. We would like to design a heading angle and determine the maximum longitudinal velocity concurrently. The L1 adaptive control solution is given here. I won't go through the detail, but I'll just explain the essence. So what it does, given a system, we design its state predictor using the difference as an error signal. We have estimation loss, and then using these estimated parameters, we design a low pass filtering structure to build the control law that goes both into the system and the predictor. This L1 adaptive controller has been implemented and commercialized across a few industries. We have a book. So in case if you are interested, here is a time history of it. We have been flying on NASA's Airstar, which is subscale commercial Boeing 757 model. Then we had lots of commercializations for Raymarine Evolution Autopilot. We had hydraulic pumps of Caterpillar. We had MBDA, Eurocopter, Seagate projects going on. We had Raymarine, Boeing collaborations, and we had Learjet F-16 flight tests. Later now we are doing safe learning with L1 adaptive control. In case you are interested, I can show you the Learjet flight tests just to see how the pilots are using it. So you should have the voice. This is an accident that happened in 1967. Luckily, the pilot survived. And when we go to Edwards Air Force Base, they have the accident data that they can load on the airplane and turn on our L1 adaptive controller to see how it behaves. And we can see how our controller can handle this type of accident. So here it is. Now they load the accident data and the safety switches come on. This is a test aircraft. They can test any condition they want. The safety switches will save.
I can't even control the airplane. You have the airplane?
And now they will test the same condition with our L1 adaptive controller.
Hey, task in 3, 2, 1, now? So you can feel there in high frequency, I made some high frequency inputs, excited the roll. Lower frequency, the roll, overshoot, or oscillation tendency is less.
Sounds good.
There's still some there. Pitch, I'm having no issues. Fine tracking and gross tracking are very good in pitch.
All right, and I have maneuver complete.
Now they have engine out tasks, which are very interesting how they shut down the engine and they're still able to fly it.
All right, recording on in ready, hack.
Running. Okay, power's coming back.
My hands are free.
3, 2, 1, now.
Controls fixed.
And recover, please.
Okay, and recovering.
Power's back.
I'm ready to try this now with with a pilot correcting for it. So
Okay, I'll give it about 1 second of reaction time. I am on conditions.
all right, and then recording on my call. Ready, ready, hack.
On. Okay, power, it'll be left throttle.
Okay.
In 3, 2, 1, now.
1 potato and recovery.
And recording off.
Okay, recording off, matching throttles.
I'm ready for the recording on ready, ready, hack.
On. Okay, left throttle coming back in 3, 2, 1, now.
I'm not touching the controls.
Nice demonstration.
Yeah, check that out. About 3 degrees of left bank.
Speeding in the rudder to match, I can feel that. It is descending a little bit, but it's...
Yeah, descending a bit, but that would be easy to compensate for.
Yeah. Okay, I think you got some good data there.
All right, recording off.
Matching power, recording's coming off.
So I always tell my students that in real world, there is no 0. 3-degree degradation was already pretty good result for us to be happy. Now what we're trying to do, we're trying to implement this L1 controller in this car scenario when they are connected over the cloud network. So our complete solution idea includes analyzing the propagated uncertainties. So we have FRRF, that's the resilient filtering, as I said. So it will produce the minimum bounds of the cornering stiffness. So that's an estimation algorithm that is going to give us an estimate of the cornering stiffness with 95% confidence interval. So we will have an idea of the range of uncertainties. When we have the idea of the range of uncertainties, we can implement the uncertainty model for the L1 controller design. So the L1 controller needs an uncertainty model to work so well. So we need a common Lyapunov method. So velocity should be concurrently designed with L1 adaptive controllers. So only need to check for the minimum and maximum velocity. And we need to maximize utility velocity. So this is the L1 condition that we'll need to verify, okay? Maximize utility, performance guarantee, and robustness guarantee. So here's the simulation for that bicycle model so far. We would ideally love to have a good car simulator where we can test this algorithm. This is the raining condition on the left, and on the right, it's the snowing condition. As we see, so the proactive control maintains desired transient and the steady state performance for all environmental conditions. And the velocity design program provides maximum safe velocity. And it's a curvy road, as you can see. So now the next. So what do we want to do? We want to move to the reactive level. So what's happening on the reactive level? On the reactive level, we want to be able to learn and minimize the model mismatch, because until now we had no learning. We had estimation and robust compensation, which had somewhat conservative approach in it. But as we learn, we should be able to minimize the model mismatch and to be able to have less conservative behavior, so more smooth approach. This work actually, whatever I'm describing for this reactive layer, is supported under our AFOSR and NASA grant. It's not supported by your effort, but it nicely fits into this framework that we can integrate our AFOSR and NASA work-based solutions into this car framework and show, for example, how it works. So what you see when we bring in the learning, for example, if the quadrotor had to traverse this forest and it does the learning, it can find the narrow path and the traversal can be reduced from 27 seconds to 14 seconds because it finds the narrow path and it can just take the risk to go there. And safety remains decoupled from learning, so it feels safe while going here, the same level of safety as it felt here. The same here. For example, if the car had to go between 3 and it would collide with all 3, if we do no learning and try to take the safe path, it will go around them. But if we do the learning, right, say the car had to go in between the 3, it will collide here. So if it tries to go the safe and conservative way, it will go around them. But if it does the learning, it can safely and confidently take the path in between without the collision. So this is what our RL1GP architecture would ensure. So, and this is planner agnostic. You can do it with any planner you want. So our work from this DoD and NASA funding can very nicely influence the progress on this grant as well. That's why I decided to combine the results and to show. So now getting back to this work, we have taken this direction. We're part of a big team, which is an NSF AI Institute grant. It's called TRACE, Trustworthy Autonomy Systems, and the full proposal is due in May. Now we are finishing one of the last stages that's due in January. And we're trying to have this end-to-end certified robust vision-based control, where we are bringing perception, controller, and vehicle, all these stages together to have the optimal balance between utility, robustness, and performance. This paper is in progress, and this STII effort, where we did already so much on this FRRF design, some of this integration work, we have papers out, we are going to integrate towards end-to-end certification and have a paper and kind of contribute to that grant. So UIUC is one of the partner institutes. So the planning grant is coming to an end, and we are in the process of putting the full proposal together. So the future work would be the certified AV control. So certification for filtering, planning, driving, vision obstacle detection, for large uncertainties like uncertainties that exist with adversarial cloud data, mission uncertainty, aggressive driver, malicious perception sample. And we have collaborators. So happy to acknowledge your grant, happy to acknowledge my collaborators. I am right at 22 minutes. I think I started with 2-minute delay, so I didn't take extra time. Any questions? I guess I'll take them by the end, huh? You said.
Thank you, Professor Hovakimyan. I think if you don't mind, we'll pause the questions until the end after Professor Wang. But thank you so much for the nice presentation and nice work from your group.
Thank you. My pleasure.
For our next presentation, we have Professor Shenlong Wang. He is an assistant professor at the Department of Computer Science. His research interests include computer vision, robotics, and machine learning. His recent work involves developing robust algorithms for self-driving vehicles and making autonomous vehicles more reliable and scalable. He received his doctorate from the University of Toronto. Professor Wang, the floor is yours.
All right. Can you hear me?
Yes, and we can see your screen as well.
Great. Yeah, thanks for the kind introduction. In today's talk, I'm going to present how to build a realistic, safe, and scalable platforms for training and validating self-driving autonomy. So as we believe, self-driving vehicles will eventually provide safer, cleaner, and more convenient transportation in our future. That being said, to reach this goal, it still requires years of effort to deliver the fully autonomous system that everyone can trust. In my opinion, there are several remaining desired goals for us to achieve this towards full self-driving autonomy. Firstly, our self-driving vehicles need to be flexible enough to interact with human traffic participants and handle the uncertainties associated with human behaviors and intentions. And secondly, self-driving cars need to be robust enough to handle rare and unseen events. Even if they cannot handle that, at least they need to stay safe and ask humans for help. And thirdly, we need our vehicles to scale up to the full world across geographic boundaries. And in the meantime, we need to maintain a reasonable price for scaling up our technology. And lastly, we need to have verified safety for our technical components in the form of both theoretical certificates and empirical findings. While it is crucial to design new autonomy algorithms towards solving these challenges, in today's talk, I want to focus on another important topic, that is how could we build tools and data to evaluate self-driving cars' performance and verify its safety. So I believe our evaluation environment should also have following 4 capacities corresponding to the 4 desired properties of autonomy. Firstly, since we expect the autonomy to interact with other traffic participants, this requires our evaluation environment to be also a reactive, to include actors that can interact with the self-driving cars, just like what we humans do. And secondly, since we expect our self-driving cars to handle rare cases and safety critical scenarios, our verification environment should include such scenarios for the autonomy to test. And thirdly, if we want to deploy autonomy at a large scale, we also need scalable evaluation platforms. And lastly, since we want to guarantee safety in the real world deployment, the testing environment should be as realistic as possible. While there is no golden standard to measure the performance of self-driving before deployment, but so far we typically use 2 different ways for verification. So one common approach is to build a test track like our IACT effort with reproducible safety critical scenarios. It is realistic and it can test the real software and hardware system, but it's limited in how many cases that we could test and could potentially bring harms to the system if failures might happen. And another solution is to use computer simulation. So computer simulation is easy to scale and we can run as many tests as possible. And we know that testing is safe as everything is running in computers. But current industry and academia solutions still has a pretty significant realism gap. So our goal is to leverage the best of the 2 worlds. We want to develop realistic, safe, hardware in the loop and scalable tests for self-driving cars. Before we go into detail about our efforts, I want to firstly quickly revisit what a simulation system typically consists of. So typically it has 3 crucial components. Taking color as an example, it requires 3D artists to build 3D assets like those static environment and dynamic objects such as cars and pedestrians. And it will also require traffic specialists to design testing scenarios and develop rules for the actor behaviors. And finally, it requires game developers and simulation developers to develop engines for animation, for controlling, and for rendering. But as you can see, despite being expensive, small scale, it cannot provide high fidelity. So one of my group research focused on closing the reality gap between the simulation and the real world. So our philosophy is to design scalable and realistic simulation by leveraging real world data and machine learning techniques. So towards this, we have made progresses on all 3 aspects in building 3D assets from real world, creating scenarios and simulating realistic sensor data. So due to the time constraint, this talk will briefly cover how we can simulate traffic scenarios and focus on how can we simulate realistic sensor observations. And finally, I will give an overview about our ongoing efforts in terms of how can we bridge the virtual world and the real world for better evaluation. So in order to simulate, we firstly need to create realistic traffic scenario, specifically given the self-driving vehicle's current state and the map of a surrounding area. So our goal is to generate the layout of the actors in the scene, which is a task that we call traffic scene generation. Here, the self-driving vehicles is shown in red and the other vehicles in blue, pedestrians in orange, and cyclists in green. So there are 2 major challenges here for traffic scenario generation. Firstly, the traffic scenes are highly structured. So we need the generated scenarios to be realistic and reflect the complicated interactive traffic rules and our common sense knowledge about driving. And secondly, given the input, there are infinite numbers of output possible traffic scenarios. So we need a generation process to deliver diverse results given the same input. So towards this, our approach is simple and straightforward. at each step in the generation process, we take the current layout as an input and compute a distribution of the next actor. And then we sample the new actor of this distribution and put that actor into the scene with its proper attributes, such as location, type of the actor, orientation, velocity, etc. And then we can repeat this process iteratively, composing the scene by generating one actor at each time. At some point, we'll decide to stop and end the generation process. So here we visualize our iterative generation process, which we've slowed down for demonstration purposes. So note that our method is able to generate traffic scenes that reflect the complexity and diversity of the real world. Just like, for instance, those parallel cars here on the left and the rightmost lanes, and a group of pedestrians that are on the sidewalk. Note that there is no rules or no heuristics. It's purely learned from our data observations. And here we show our method could produce a scene in which two cyclists perform unprotected left turns. And our method can also produce diverse traffic scenes given the same input. So here we show two samples from our approach. On the left, we see that pedestrians are crossing the intersection, where on the right, we see a vehicle that is completing a left turn, which demonstrate different traffic light conditions. So we also quantitatively compare our scenario generation against a variety of baselines for traffic generation, including both heuristic method or grammar-based method or learning-based method. So in terms of different metrics, for all metrics, the lower the numbers are, the better the performance is. Overall, you can see our scenario generation outperforms most of the competing algorithms in terms of both likelihood and the divergence. So one of our application of this, generative model is to find rare traffic scenes from the real world data, such that our method thinks that this scenario is less likely to happen. Here we show an example that we identify a rare scene from 1 million different frames of the real world data recordings. So our method identify a rare case where an actor is conducting an illegal U-turn, which could be potentially used to select useful data for us to train and test our autonomy. So after we create novel realistic scenarios, we also want to render them out and produce realistic sensory input to autonomy for testing. So this is a task of sensor simulation. For instance, how could we test if the perception system would detect a vehicle if we add it here? Well, testing such situations in the real world might be too costly, risky, or even impossible. So camera simulation can help. It can also produce additional training data to better handle those situations. However, current methods are not realistic enough and cannot handle millions of scenarios. So our work leverage a technique called insertion rendering from AR, from the domain of augmented reality to tackle that. To give a brief overview, we reconstruct 3D assets from the real world data and then insert the dynamic object into the video sequence. The results are expected to be realistic, geometrically consistent, traffic aware, and scalable. Now let's take a deeper look at each step. So we develop a neural network that can reconstruct accurate textured models in the wild from images collected during driving. So we build a large and diverse asset bank with over 8,000 unique vehicles. So using the reconstructed mesh, 3D mesh, we can perform novel view rendering as I show here. And we now show how GeoSim leverages those assets library to insert actors and simulate new images. We firstly automatically generate a plausible placement using our scenario generation algorithm that I described before, and also produce a trajectory that complies with existing traffic. Then an asset is randomly selected for rendering. We then render the selected assets like this car at a new target pose. We account for occlusion by reasoning the dense depth map predicted from our LiDAR and camera sensor. So putting the object into the scene will also result in casted shadows and change of the shadings in the background. So we can count them by render them inside a graphics engine to obtain the soft shadows and composite those shadow map into the image as well. And finally, we perform some post image composition to further retouch the final image. And we use a synthesis network to handle the inconsistent illumination and implant the discrepancies at the boundary so that the vehicle fits the environment seamlessly. So here is an example of our final approach applied to video simulation. In total, there are 4 simulated vehicles here. One is the hatchback that is driving towards us. The other one is a car that is stopped at the left turn. And the other 2 are the 2 cars that are crossing the intersection. As you can see, those inserted vehicles obey the traffic and have reasonable motion and reasonable appearance. Here is another example. So unlike the 2D approaches, we can simulate consistently across reasonable long time horizons. Notice the car that in front of us. Our method could also allow us to simulate different appearance. For instance, that car has a braking light on when it's decelerate. And it's worth note that the 2 cars that is driving towards us, the blue car and the sedan that is driving towards us are also simulated. So here is an interesting scenario that we intentionally simulate rare cases that 2 vehicles are running the red light and cutting to the police car's lane, and creating an interesting scenario that we don't often see in the real world. So being 3D aware in the simulation also means that we could do multiple camera simulation that is physically plausible. So here in the top view that shows one of the side cameras, on the bottom we show the main front facing cameras. The 4 vehicles simulated by GeoSim are consistent across different cameras in terms of appearance and shadings and behaviors, etc. So here are some additional qualitative examples. So I want to pause a little bit and for the audience to guess which vehicles are simulated. So as you can see, there are quite a few vehicles there. And here is the results that those vehicles are not real. So as you can see that we can handle diverse scenarios and also handle proper occlusion between different objects and also between the object and the background and the diverse lighting conditions. So we also conduct some visual comparisons that show that our approach significantly outperforms either graphics-based rendering method or 2D image synthesis method. And our user study also suggests that users like humans that strongly prefer our methods to be more realistic. And further, with GeoSim, we could obtain costly free annotations for training neural network for perception, which significantly improve the performance across multiple segmentation networks, which I will not go into details. So our camera simulation is generalizable to different geographic areas and configuration and camera configurations. Here we show some results in totally different data sets that captured in Miami, which is we never seen that during training, and also with different cameras. So as you can see, it's still quite realistic results and showcase that it's preferred over the CAD model plus graphics rendering method. So in summary, we present a neural autoregressive generative models to create realistic traffic scenarios and a geometric guided simulation framework that can achieve great realism for object insertion. So both papers are presented in this year's AAPR. And what is our next step? So far, we have seen that how our research could boost the realism of the self-driving simulation. So in simulation, there's still a fundamental gap that can hardly be closed without taking the full real-world system into consideration. To be specific, in the simulation world, autonomy is interacting with the virtual environment. That means our physical world and mechanical systems are out of the testing loop, which is not ideal. To overcome this, in our STII-funded project, joint with Professor David Forsyth from the computer science department, we are exploring a new validation paradigm that blends the virtual safety critical scenarios into the real world with onboard hardwares. So specifically, you could consider that we have the self-driving cars to wear a pair of AR glasses. And specifically, suppose our car is driving on an empty test track and we plan to create testing scenarios with virtual actors having some risky behaviors. And we can seamlessly insert those virtual events into real images perceived online from the physical world. And then we expect the resulting composed image to be photorealistic and physically grounded. The manipulated images are fed into onboard autonomy, allowing us to test the self-driving vehicles to see whether they react to such virtual events correctly, but within a real world test track and like IACT in future and real hardware system, like our Illinois EV platform. So this project's final goal is to develop a new safe hardware in the loop and cost-effective test for self-driving cars to respond to immersive, safety critical traffic scenarios. As we could imagine that we could reliably test any safety critical scenarios with our real cars, but nothing will be potentially harmed, even if the testing fails. So the project is still ongoing, and we look forward to share more results and video footage of the real world test prototypes, hopefully early next year. All right, and they summarize the peer review conference papers that we covered in the talk. And I would like to thank my collaborators, students, co-authors, also STII to provide the seed funding opportunities, and NVIDIA to provide the hardware donations. And I'm happy to take questions. Thank you.
You say that was a brave scenario with two vehicles and a patrol car, as you mentioned, something that we won't see in the real world. So I guess we can open now for questions, and I'd like to remind the people who joined via Zoom to please feel free to type in the chat, and be happy to ask the questions for you, or you may unmute yourself as well. So questions? I'll start. Professor Hovakimyan, if I may ask you, so with the examples you mentioned, the architecture was tested for bicycles and car. I was just wondering, what are the required changes to the architecture of the controller if we integrate freight trucks?
So if we want to integrate it with a car, we have to implement it for a car model. And as far as I know, so my postdoc Hunmin is here, who has been doing the work, and also the student Wenbin, who has been working with him on the paper also to put it on the car. So we didn't have a car simulator model, or we were looking for a good car simulator model to do it. And I don't know how far they went. Wenbin, Hunmin, could you update how far did we go in terms of finding that car simulator model to demonstrate the algorithm? If one of you could comment on that.
We are not working on this part, but the major difference, basically the bicycle model is a simplified model, which is widely used in the car control community. So this is quite accurate. Yeah, even we apply this control law into the real car model, the performance will not be much difference.
Right, but they're interested in seeing if they could test it, right? I guess you have a car maybe on which you would like to test it, right?
Yeah.
So Hunmin, would you be able to go to their facility and do the experiment on the car? That's the question.
Yeah, I think we can do that. Yeah, we can apply our controller to test the real car model. Yes.
I guess the answer, the way to interpret is that by using the bicycle model, we're confident that it will work on the car because it's quite common to use this bicycle model in these car simulations and car research. It's common to use this bicycle model.
Yes, that's correct.
The algorithm. That's what Hunmin is trying to say, that what we have tried is not uncommon to test the value of the algorithm. If it would work for a car, people do it quite often and then it works. So we're ready to come. If you have a car on which you would like it to be tested or a car simulator, we're ready for that. Just help us get integrated. You know, the pandemic didn't let us to have lots of in-person meetings and to do this experiment, but we're absolutely ready right now. If you tell us, here is the car simulator, come and try. Wenbin and Hunmin will come and try.
Got it. Thank you. And then if I may extend, with the proactive and reactive architecture, is it possible to extend that to account for like a network-wide information? Because I think in the picture, the reactive level was mainly the surrounding environment of the vehicle. I guess the main question is if the unforeseen event is in 2 miles ahead, how can that information be integrated where the control is assessing a more network-wide information, so the driving will be safe later in time?
Yeah, maybe I can answer the question. That one, for the proactive level, basically can deal with this situation. So the proactive level is what proactive level is doing is the preceding vehicle share their road condition information with the following vehicle so that the following vehicle can react and prepare the new environment. And the reactive level is more, it's more reactive. You first need to hit such road to learn more precise the environment. So yeah, proactive level will deal with this large uncertainty, and the reactive level will deal with the small size uncertainty.
Thank you. Additional questions for Professor Hovakimyan? Okay, I think we're waiting. If I may start with Professor Wang. So as you mentioned, it's the extent of the database to do the fidelity simulation of the objects or the actors is really nice. So my question is, as we're anticipating new vehicles like electric vehicles, and some of those information to fundamentally simulate those vehicles in your model may not be available. How do you integrate those technologies when you don't have the data? And we may anticipate that the behavior of these vehicles will have an impact on safe driving.
So let me see if I understand your question. So your question is, how can we integrate those technologies if we don't have the large data to create the assets?
Yes.
I see. So I think the answer is nowadays we have a lot of open source self-driving data sets that we could leverage. I think the data is not technically a big big problem, although there will be some domain adaptation, say whether we can leverage data collected in Germany and build those assets and test it on our Illinois test track. I think that is possible, but that means there will be some domain gap, right? So in Germany, the cars tend to be smaller, or they might have different type of cars that could result in some domain gap. That being said, I think there are a lot of opportunities there, and in the meantime, we also develop some technology that allow us to collect our own data. Say, suppose in the future that we have the test track and we can drive our own self-driving vehicles to collect those data and build the virtual environment for us to train and test. Yeah.
And in your example, it was daytime. So I was wondering how you may handle a nighttime scenario.
That's a very good question. That is one of the open directions that and not only just different time of day, but also different weathers, different seasons. It's a little bit more complicated. We need to build the 3D assets to be able to relate, right, and also account for some changes over time. So I think this is a quite active topic, and both Professor David Forsyth and we are pushing towards some of the directions in terms of leveraging large unsupervised data from the internet to try to help with that. So the general concept is, suppose we have an image that's taken in Illinois campus, although we don't have exactly same data of, it's summer, it's winter, it's daytime, it's nighttime, but we could find a lot of similar images that from the internet that's taken at a different time of the day. And we could leverage and incorporate those appearance changes and transfer those appearance changes to our images that are taken at daytime of the Illinois campus. So this is a general concept, proof of concept, and we have made some progresses towards this direction. That being said, it's still a nice open direction that we want to explore later towards building a full relatable 3D representation. Yeah.
And I think as we're planning IAC, it would offer a nice opportunity to fill in those gaps, and we'll have that controlled scenario that can feed into the nice work that you and your group are doing.
That sounds good. Yeah.
Any additional questions? Okay. I don't see any more on the chat as well. Again, I'd like to repeat that thank you so much for sharing your nice work and research. I'm really excited as you close out this first round of SCI projects. We look forward to the final reports, and also keep in mind the critical use cases that you'd like to integrate, right? It's the wish list that we'll have to incorporate as we're planning the design and construction of IAC. Thank you so much. I'm really glad to close out the Kent Seminar Series with both of your Professor Hovakimyan and Wang's work. With the audience, please help me thank our speakers, and have a good rest of your day, everyone.